This is a continuation of radioactive decay, okay? So this definition will आगे to just note them down, and then I'll start with the equations. There's a page where it says radioactive decay. 23.2. Are you done? Okay, just a quick reminder of last class. Short screen record. We'll be done with this topic today. And I'll let you solve some questions. I want to start medical physics from next class. Okay, medical physics. We're more or less down to our syllabus. The day we finished our astrophysics, the part in next tomorrow. 1 week we'll finish medical physics. Astrophysics is now in 2 classes. So 2 weeks from will be done. I also want to take a mock on paper 5, but paper 5 will go again. Do you guys have year-wise paper 5 paper? Oh, sir. What about the rest of you guys? Do you have paper 5 year-wise? I'll be doing 5 years. 19 to 24, all papers. On paper 5, there's nothing to teach. It's basically practicing. Okay, so I'll do as many as we can. Also, paper 5 to planning. It's essentially just I'll teach you the format and then we'll do them. Paper 5, which is second question is a problem. The graph analysis. Paper 5 is no. I mean, if I gave you a question right now, you should be able to solve if you know the process. Let's see. So a analogy to back query, we need to use this to derive some equations out there. So do you remember what this was all about last class? So I'll just go through this one more time. It's basically a crane that's used in these fairs where you put the crane inside, you can pick up things, right? And this crane here is trying to pick out these spheres from this box here. A box ball and the thing is, it can't pick up all of them. So every time you put the crane in, how many can it pick up? So it turns out there's actually a probability. Okay, so it's a random actor process, but there's a chance that at any given time, out of all the spheres available, how many do you get out? 1/10. Okay, probability is 1/10. So if there are 100 balls here, and you take this and then you place it inside, right? How much do you think should be able to be taken out at first go? So probability is 1/10. Basic probability. Do you guys know that if the probability is 1/10, and if you have 100 of them, how many of them will be removed? 10, right? So your 10 of them gets removed here. How much is left? 90. You put the crane back in, and the proper bear has to say how much is coming out? 1/10. So you have quite a bit of it. 9, right? And you go back in, our 8 bear hobe, you back in 7 bear hobe. The reason why it's getting lower and lower, these numbers, is because the number of spheres that's inside the container is becoming what? Less. But you'll find that throughout this whole process, there's one thing that remains the same. What is it? The probability. It's 1/10, 1/10, 1/10. So throughout the process, probability is same, but the number of particles that are coming out, right? So radioactive decay is exactly the same thing. I know it might not seem right away, but radioactive decay is that when you have an atom or a sample, and there are millions of unstable nuclei, right? how many of them actually decay? So there's actually a probability of that. There's no guarantee that this will decay. There's a chance that this will decay. And every nucleus has a chance that is fixed. So uranium to the nucleus name, let's say I take a uranium-235 nucleus. It is unstable, right? What will it do to become stable, undergo radioactive decay? What are the chances of it undergoing decay every step? It's a number. It's a very small number. Okay, and it means that if I give you 1,000,000 of uranium nuclei in front of you, the probability to the 1 by million. That means out of all the million that you have, how many will decay? Only one. Which one we do not know, but definitely quite a decay will be. One. So that's why we can't pinpoint which particles decay, but we can very accurately predict what though, that there will be how many decays going on. So radioactive decay problem we can't pinpoint which nuclei decays when, but we can see the bigger picture and we can find exactly how much will be left after a certain decay. So I can't predict. It's impossible. Mathematically, it's impossible for you to predict this red color ball here. But isn't it true that throughout the whole process, there's a time when this will decay? And if I keep doing this again and again and again and again, wouldn't all of them eventually just go away? So isn't there a number of times when this thing decays? Last class I showed this using what? The coins. Again, if you keep flipping coins, right? Heads and tails. And let's say there's one red color coin out there. Heads and tails, wouldn't there be a time that the coin will disappear, right? But is it possible for you to predict when will the red coin disappear? No, right? So yeah, basically the main thing I want you to understand here is that radioactive decay is actually a probabilistic process. There's nothing guaranteed about it, right? And if there's probability involved there, what's the probability? So a probability data of decay is what I just ended last class with. It's a quantity called the decay constant. And this is the single most important quantity in radioactive decay. This determines how something decays. So if your probability is very large, right, it'll be a very high radioactive element. On a high probability, it's undergoing decay very rapidly. If your probability is very low, right, it'll take a lot of time. So probability of uranium is extremely low. That's why uranium has a half-life of like 200 million years. And every 200 million years, তোমার স্যাম্পলের যতটুকু radioactive particles halfway যায়. That's really slow, right? So ওটা decay constant বের করে দেখবে, it's a very, very small number. Okay, so what are we going to do today? So আজকে যেটা করব is I will derive the 4 equations of radioactivity. So radioactivity মধ্যে হচ্ছে 4টা equation. এই 4টা equation দিয়ে you can solve any radioactive question and every radioactive question out there. Okay, so let's start with the first one. So number 1 these are radioactivity equations. All right, so number 1, the most important one, মানে এটা দিয়ে স্টার্ট করি আমরা সবাই স্ক্রিনে দেখো, activity of a sample. Okay, how do you find it? So the activity of a radioactive sample is equal to এটা কেমনে ডিরাইভ করবে এটা দিকে দেখো. Can you tell me যে এই ডায়াগ্রামটার মধ্যে what determines or what represents activity? যে এই অ্যানালজির মধ্যে what is the activity? Yeah, the number that's removed, that's activity. How do I find the amount removed? Can you tell me কেমনে বের করছ এখানে? Number of particles removed is equal to what? Yeah, that very good. So total number of particles left into the what of the particle, the probability, right? So activity is equal to the total number of particles available into the probability, right? And that's exactly what the equation is. So activity is equal to total number of particles out there, which we represent with capital N, into the probability of decay. What is that? Lambda. Okay, the decay constant. And এখানে একটা minus sign রাখো এখানে. The minus sign is symbolic. You do not use in your math. The minus indicates the fact that the activity is always what? Decreasing. It cannot increase. Okay, so activity equals to this one. There's an alternate version for activity because অনেক সময় হচ্ছে এটা নিয়ে MCQ না মানে 1 mark question আসে. Activity is also dN divided by dt, number of particles per unit time. Okay, and what's the unit for activity? In our syllabus there are 2 of them. We mostly use becquerel, BQ, or there's an alternate out there. If it's a very small, slow decay, we use CPM, counts per minute. Becquerel ki hobe? Counts per second. Do you remember Becquerel? So যদি না মনে থাকে প্রবলেম নাই, এটা O levels অত prominent ছিল না, but radioactive decay হচ্ছে SI unit is Becquerel, BECQUEREL. It's a person's name, and it's per second basically. So physics say there's a lot of per seconds out there. There's 1 by second, যেটাকে আমরা hertz ডাকি, frequency. This is also 1 by second, so it comes a different ভাবে ডাকি. What do we call it? Becquerel. Okay, BQ. So yeah, activity equals to minus n lambda or lambda n. Is that okay so far? This is the equation, first equation. Second equation is, remember the radioactive decay graph that we had? And I told you that there was actually a system to this. It's not random. So it turns out this activity that you see here has an equation. Thankfully, the equation is derived, you just have to directly know the equation. The equation for radioactive decay will be something that you can relate to because you have seen similar things before. It is the exact same equation as it's the same equation as your capacitor decay. So discharge. Do you remember the equation for capacitor discharge? Q equals to minus. Very good, right? So that's exactly the same thing. I can just like a small difference of it. Activity is equal to A naught e to the power minus lambda t. So the difference is instead of t tau there, you can lambda use for A equals to A naught e to the power minus lambda t. That's basically the equation of that graph out there. So we used to think it was random. Then eventually after derivation, we found that it's not random. The radioactive decay overall process is actually a very systematic process. It follows the exponential decay curve, similar to discharge of your capacitor. Okay. All right, A equals to A naught e to the power minus lambda t. Now, এখান থেকে আরেকটা জিনিস আমরা derive করতে পারবো. Like we can further break this down. Previously, what did we see? A equals to this upore, A equals to minus lambda n, right? So can I not replace A with lambda n? So if I write down here n lambda, so there's n lambda here, should be equal to what? N naught lambda. N naught key represent for a number of particles initially. I hope you know what A naught is as well. A naught is initial activity, right? So lambda times e to the power minus lambda t. Ekhane theke ki cancel out hoye jabe? Lambda, which means if you want to know the number of particles that are left in your radioactive decay process or number of particles that are available, you can also use this equation. And this is the reason why there was like a small confusion with the half-life definition was the average time taken for a sample's what to become half. Number of particles, activity, mass, সবকিছু. And you sometimes students wonder how is everything possible. It's possible because activity depends on the number of particles you have. Number of particles is the mass that you have. So mass, number of particles, activity, they're all actually changing in what manner? Same manner. So they're actually interchangeable. Okay, times e to the power minus lambda t. So yeah, that's your second equation. The third one, I mean, to গুছাই করে দিব তখন কপি করে নাও. The third one is actually a small derivation. Derivationটা হচ্ছে, and this third equation is the one that matters the most. I'll tell you in a minute why. So we found in radioactivity that when you have a sample and the sample decays, the time taken for the sample to decay, right, to become half its initial value is actually fixed from all levels, right? What was that time called? Half-life. So half-life was the average time taken for a sample's activity or mass or number of particles to become what the original value, half the original value, right? Now, you might also know that there's a similar number that exists for capacitors. What is that called? Time constant. Time constant is the time taken for a capacitor's charge voltage to become what? 1 by ETH, the original value, or 37% of the original value. Remember? Right? So this exists. Now, we're going to use that to our advantage. See what I'm going to do right now. So if you look at this graph here, and you have your activity A naught at the start, the time taken for your activity to become half is going to be referred as what time? Half-life, right? So half-life ta constant thake. So this time here is called T half. So আমরা যেভাবে লিখি, this is how we write it, T with a subscript half. That's basically half-life, right? And your activity was originally what? A naught. What did it become here? A naught by 2. Do you follow? If we use this idea, we can come across this equation here. Equation ta hocche A equals to A naught e to the power minus lambda t after half-life, after one half-life, right? So after T equals to T half, can you tell me what should the equation be? How does it change after one half-life? So A is going to be equal to what? When I'm doing one half-life cover query, what would these values become? Yeah, A would become A naught by 2. So A naught by 2. And A naught times e to the power minus lambda. What should this T become? T half. So what I just did here? What I did here was I waited a time that is equal to what time? The half-life. So if I wait a time equal to half-life, wouldn't my activity become half the original value? So that's what happened, right? If we simplify this, see what happens. A naught cancels out, and we end up with half equals to e to the power minus lambda T half. Now, how do you get rid of the e function here? Yeah, by taking natural logarithm, right? So ln 2 to the power minus half equals to ln e to the power minus t half. Do you agree? What's this going to be? Ln 2 to the power minus 1 minus, yeah, and eta ki hobe? Minus lambda t half. And from there, this one equation that you will have to use for every radioactivity question out there. Now with your question, right? Just use this, you'll get 1 mark. The equation then eventually turns out to be lambda is equal to ln 2 divided by t half. Why is this equation so important in radioactivity? The reason behind this is, if you see the other equations I've derived so far or provided you, all of them contain what function? Lambda, right? Which means that lambda chhara kono question korte parbo na. You can't do a question without lambda. How do you find lambda? If I give you a radioactive sample, right, how would you know what the lambda is? Because unless you know the lambda, there's no way going forward. So the way you find lambda is by finding the what of that sample. Half-life. Half-life very too easy. You allow the sample to decay, you find the time taken for its activity to become what the original value. How the original value. Once you have lambda, you can start your question. Otherwise, every single equation that we have will require lambda, which is a decay constant. Okay, so lambda ta ber korar jonno half-life ta lagbe, and as it goes, proportional lambda deয় না। তো ওরা সবসময় কি দেয়? Half-life দিয়ে দেয়, and they want you to find lambda. Bear in mind couple of things. Half-life এর যে ইউনিটটা, lambda ইউনিটটা same হবে। So if your half-life is given in years, your lambda is per year. আচ্ছা, মানে ডিকে কনস্ট্যান্ট ইউনিট কিন্তু per second। আর তোমার যদি এটা সেকেন্ডে দেওয়া থাকে, এটাও সেকেন্ডে থাকবে। Just remember that lambda and the time that you have here have same units. Okay, so that's something you have to keep in mind for calculation purposes. So yeah, that is these are the equations of radioactivity. You can solve any radioactivity question based on that. Before I give you the equations in a proper way, there's a couple of things I want you to know. Your activity is obviously the activity at that moment. When you find the number of particles, right, what does that tell you? The number of particles that decayed or the number of particles remaining? Yeah, so the equation, it includes capacitor. I've seen some problems. Capacitor, when you do the math, like, Q equals to Q naught e to the power minus T by RC, right? That Q that you get is the charge that's decayed, discharged, or the charge that's left. It's always left. Okay, এখানে হচ্ছে n activity. These are all the activity or number of particles that remain, but they can ask you how much decayed. How do you do that? Yeah, original minus this, right? It was there in your O levels. তোমরা যে half করে করতে না ম্যাথটা 1/2, 1/4, 1/8, right? তারপর বলতো 1/8 এর পরে what is the amount that decayed? It's 1 minus 1/8. Because 1/8 always meant what? The amount that remains. So these small things are some things that you have to look out for. Some other things that you have to be aware of is because A2 তে যেহেতু radioactivity দিচ্ছে, there must be some catch out there. Catch একটা এটা, আর একটা catch হচ্ছে you need to be aware of the fact that the sample might have what radiation involved in it, background radiation. So to do your calculation, all of these calculations, you need to watch your sample, correct the activity. How do you correct your activity? Yeah, you subtract the background radiation and then do your math. Okay, always remember that the equations are only valid for corrected activity. Corrected mane hocche you have gotten rid of your background radiation. Do you follow? Okay, so yeah, these are your equations and equations গুলো দিচ্ছি একটু on. Okay, note them down. Equation if you can solve questions successfully today, we're done with radioactivity. Okay, I really hope exam radioactivity ashe আর এইখান থেকে আসে, not from nuclear physics. ওটা আসলে actually problem নেই, but এগুলা freebies মানে এখান থেকে এই question আসে, they're very easy. Some of them are given in the paper. Yeah. Question যে equation page থেকে একটা ওইটা দাও. No, so lambda is 1/t. So if your half-life is in seconds, lambda is per second. Yes, exactly. So the lambda, let's say I get a lambda value of 5,000. What does it mean? Every second, there's a chance of 5,000 particles being emitted from this sample. Mm-hmm. Last one, the one in the box. It is challenge. A levels, if you can remember formulas and equation, you get like 60% of the marks without doing any questions. So it is a challenge. Flashcards on the world, like small cards with the equations in them. So every time you get a chance, just go through them. Take point, it'll show up. So 60% of the formulas. ওই একটা বুকলেটের মতো মাউথ করো where just every chapter equation গুলো লিখে রেখে পাশে when to use them, ওইটা যদি বারবার রিভাইজ করতে পারো, that should be the main focus and definitions. And notice the total number of particles originally available in the sample. Right. Done? Equations? Okay, try this. It's a good starter question. I'm only keep taking a sample of carbon-14 contains 56 grams of carbon-14. Carbon-14 has a half-life of 5,400 years. Find the activity of carbon-14 mass at the start. Also, find the activity of the sample after 3 years. Additionally, find the number of carbon-14 nuclei that remains after 3 years. এগুলো ইউজ করে হচ্ছে exact math use করে we do something called radiocarbon dating. It's a process by which you can find the age of old artifacts, right? ওই carbon-14 এর নাম্বারটা ইউজ করে করা হয়. So the math they do is very similar to what we can do right now. So see if you can figure this out. This is like a medium level question in your exam. Not too easy, not too difficult either. তিনটা কোয়েশ্চেন আছে আচ্ছা একটা হচ্ছে গ্রেড 9 এর কোয়েশ্চেন ফাইন্ড দি অ্যাক্টিভিটি এট দ্য স্টার্ট এটা মানে ইটস অ্যাকচুয়ালি ভেরি ভেরি বেসিক একটা কোয়েশ্চেন তারপর হচ্ছে 3 ইয়ার্স পরে যেটা বের করতে হবে ওটা একটু অ্যাডভান্স আর এটা আর টু অ্যাডভান্স সো 3 tiers of questions here. Oh no, ওইটাই বলছিলাম যে হাফ লাইফ আর ডিকে কনস্ট্যান্ট সেম ইউনিট রাখতে হবে সো সেকেন্ডে রাখতে পারো আওয়ার রাখতে পারো বা দুইটা সেম ইউনিট রাখতে হবে obviously I recommend যে you take it to seconds because that's the safest here but এখানে যেহেতু 3 years বলছে at years রাখলে প্রবলেম হওয়া উচিত না Release activity is number of particles that are released every second. What? মানে না কি সব মাইনাস ল্যামডা নিলে তো কমন কথা মাইনাস ল্যামডা টি তুমি প্লাস ল্যামডা টি আছে ম্যাথমেটিক্যালি সম্ভব না আচ্ছা করে দেই first find the activity of the C14 at the start. Could you find it? Yes, sir. Yeah, what's the activity at the start? 20 becquerel. Yes. Counts per year. 20 per year. Oh gosh. Okay. How do you do this? Shall I explain it to the echo? So the activity for your sample at the start can be very good. So activity formula A equals to lambda n, right? So you cannot say it's a 4-mark question. Mark the to better. So 4-mark, you're supposed to find two things here. First, I don't key lambda. So lambda equals to what? ln2 divided by t half-life. My natural logarithm by t half-life is how much? 5,400. So 5,400 years. So your lambda is that. Second thing better, but anyways, amra years rakhtechi. So the activity is going to be this one, ln2 divided by 5,400 into what's the number of particles at the beginning? How do you find that? Mole by mass. Yes, so 14 divided by 56 56 na koto chilo 56 into 6.023 into 10 to the power 23. It's a basic chemistry actor that how do you find, in fact physics we did this, okay? How do you find a number of direct mass? I was wondering. This is the mass we have. This is the molar mass or atomic mass, right? So the formula is what? Number of particles, mass of whatever you have divided by their relative molecular or atomic mass into the Avogadro's constant, right? So এটা চলে আসবে, এটা করলে যেটা আসে answer, but I want it to be in seconds. So how do you convert this into seconds? Into 365 into 24 into 3600. That is the activity. Can we meet এভাবে রাখলাম because অনেক সময় বলবে ইউনিটটা ব্যাকরোলে দিতে, which they will most of the time. So কত আসে এটা? So তোমাদের যে অ্যানসারটা আসছে ওটাকে ডিভাইড করো by 365, 24 and 3600. Ten to the power 12. Right. এটা আসছে না? $9.80. Yes, 9.81 or 9.8. ঠিক আছে. So yeah, this is your activity. It's a maniki. Let's put a note here so that you know what this is. It means that the sample at the moment, কি করতেছে, is releasing how many particles every second? 8 into 10 to the power 12. Okay, so sample at the moment releases this many particles. Particles গুলো কি? Oh yeah, it's alpha, beta, or gamma. We don't know. আচ্ছা এটা যদি বলে দিতে তাহলে ওটা হইতো, but we don't know for like right now কি হচ্ছে. So the sample at the moment releases these many particles. That's what activity means. Now over time, the number of particles that will be released, এটা কি বাড়বে না কমবে? কমে যাবে কেন? Yeah, because the main sample যে হচ্ছে stock ওটা কমে যাচ্ছে না, so the chances of decay কমে যাবে, right? So তারপরের question is find the activity after 3 years. So এটা definitely কি হওয়ার কথা, the number is going to be smaller, right? So let's find activity after 3 years. So after 3 years বের করার জন্য কি ইউজ করব আমরা? Yeah, that formula. Okay, after 3 years, because when it comes to time frame relationship, you have to go for a equals to a naught e to the power minus lambda t. My initial activity is 9.8 into 10 to the power 12 into e to the power minus lambda টা হচ্ছে, এখানে একটা ট্রিক দেখাবো তোমাদেরকে, একটু দেখো. Do I keep my lambda in seconds here or do I keep my lambda in years? So it depends on what the question is asking you. So if the question is asking you to find the activity after a certain second, keep the lambda in second. কেন আমি দেখাই, এই যে lambda কি, ln2 divided by কত ছিল, 5400 into what time frame are we looking for? 3. তোমার যদি এইটার ইউনিট আর এইটার ইউনিট সেম হয়, what happens? They cancel out, right? So keep their units the same. It's mandatory. So এটা সেকেন্ডে রাখো, ইয়ার্সে রাখো, but the year or the time and this thing must have what unit? Same unit. Okay, that's the most important part here. So তোমাদের যেটা সুবিধা হয় এটা ইউজ করে, যেহেতু ইয়ার্স দুইটাই দেওয়া, you can directly use years here, and এটা ইউজ করলে it'll give you the activity of the sample after 3 years. What is it? আচ্ছা হ্যাঁ, মানে বেসিক্যালি যে জিনিসটা আমরা নোটিস করি যে বেশি চেঞ্জ হয় না. 3 years is not a very large amount of duration in 5400 years of comparison. So over 5400 years, what is the sample's activity going to become? Half. তো তোমার 3 years কি would you see a very substantial change? No, right? তার জন্য দেখা যাচ্ছে না. তোমরা কি বুঝছো ওটা জাস্ট, মানে আমাদের এখানে হচ্ছে অ্যাক্টিভিটি বের করলাম, অনেক সময় দেখা যাবে একদম সেম নাম্বারই রয়ে যায়. ডোন্ট ওয়ারি, দ্যাট ইজ পসিবল. It's just that the sample is not very active. So over 3 years, কিছুই বের হয় না. Imagine your sample is so low in activity that it produces 10 particles every day. 3 years পরে কিন্তু it wouldn't change much because trillions and trillions of particles remove হওয়ার কথা, বেশি হচ্ছে না. So if your activity doesn't change much, it's fine. But if your activity changes very rapidly, what does that tell you? It's a very highly radioactive sample, okay, and shouldn't last very long. So tomar let's say plutonium, right, has a half-life, or polonium, I forgot, has a half-life of, let's say, 10 days. So every 10 days your sample is supposed to become what? Half the original value. So doesn't it mean that it's decaying very rapidly, as opposed to what? Something that has a half-life of 5400 years. What is that slow, right? Granite goldstone in last class has a half-life of 2 billion years, right? You probably never see it decay once in your lifetime. একটা particle release করার chance নাও থাকতে পারে, probability, right? So that's the thing, যে it can be like that. Next হচ্ছে find the number of nuclei that remains after 3 years. So তোমাদেরকে বের করতে হবে কয়টা particle বাকি after 3 years. কেমনে করবে এটা? N equals to n not there. So you'll redo this math with n as the number. করতে পারো. হ্যাঁ, right, দুইটা দিয়ে করা যায়. So তুমি you can do this, okay? N equals to n naught e to the power minus lambda t. Same math আবার করবা, but this time কি দিয়ে করতেছো, number of particles there. Or you can do something else, which is a equals to lambda n, right? And আমরা কোন অ্যাক্টিভিটিটা ইউজ করব? The activity after 3 years, right? So activity after 3 years কত? 9.79 into 10 to the power 12 equals to lambda টা আমরা হচ্ছে ln2 divided by 5400 এটা হ্যাঁ এটা সেকেন্ডস এ 365 into 24 into 3600 into n, and that n will be the number of particles that you have after 3 years, right? So কত? ওই যেটা সেকেন্ডস এ রাখছিলাম আমরা, একটা ব্যাকরোল ছিল না, ব্যাকরোল হচ্ছে পার সেকেন্ড। বলো 2.4 35 হ্যাঁ 24 আছে 35 তো পসিবল না। কি করছো? So yeah, that's like a typical question. Do you understand? Is there anything that you want me to clarify here? থাকলে বলতে পারো। ব্যাকরোল সেকেন্ডে থাকে এখানে। ও না না না, এই জিনিসটা হচ্ছিল একটা সেপারেট ফাংশন, এটার উপরে ইউনিটটা ডিপেন্ড করে। এটা তো ব্যাকরোল আছে, এটা যেহেতু ব্যাকরোল তার জন্য এটা ব্যাকরোল, এটা ইউনিটলেস, এটা কোনো ইউনিট নাই। হ্যাঁ হ্যাঁ Okay, so I'll give you some definitions. A topic on this definitions that you need to know. What a copy correct, yeah. No, it depends on the unit provided. So in the question, they'll tell you to give it in backrows, then you do it. Do you not think you can do anything? It's fine. All of them are fine.
So that like CP per year.
So, yeah. So instead of that, you write this year to the power -1. That's CP per year is not a unit, yeah. Or S to the power -1. S to the power -1 is what we call backrow. Okay, and there's something called CPM. That's very different. That's counts per minute. That is an official unit. But for year, you just write per year. হ্যাঁ মানে তুমি আনসার ব্যাকরোলস এ রাখতে চাও, মানে যদি চাই ওরা, হ্যাঁ তাহলে সবকিছু সেকেন্ডে রাখতে হবে। Okay, let's see the syllabus and see if we have covered everything. আমি definitions গুলো দিচ্ছি তোমাদেরকে। Understand that fluctuations in count rate provide evidence of random nature of radioactive decay. That's what we saw there. You know, it's not predictable. Overall, it is, but not individually. Understand radioactive decay is both spontaneous and random. I'll give you definitions of that. We have seen that. They're two different things, by the way. Randomness and spontaneity are not the same. Random is you can't predict when it decays, which one decays. Our spontaneous behavior is that it is something that you can influence. It happens, just happens, okay? Define activity and decay constant. So what's activity? The number of radioactive particles emitted per unit time. And what's decay constant? The probability of decay of a nuclei. So the chance of a nuclei undergoing decay every second. Okay, so that's your decay constant. I don't know if you have seen the number, but decay constant খুব ছোট number আসে, 10, like 10 to the power minus something. Recall and use the formula A equals to lambda n. That's the activity formula. Define half-life. So এখানে অনেকগুলো definition আছে. What's half-life? Yeah, it's the average time taken for a sample's activity or number of particles to become half the initial value. This one is the one I just showed. 0.693 jeta, that is what? Yeah, natural logarithm. Understand that exponential nature of radioactive decay and sketch and use the relationship that for activity, number of particles of undecayed nuclei or received count rate. So yeah, so তিনটা জিনিস হচ্ছে এখানে এই ফরম্যাটে রাখতে পারবো। So x could be your what? Activity, or it could be what? Number of particles that you have in your sample. Okay, so count rate, same count rate is activity eventually. So yeah, that's what we have here. Now এখানে এক্সপেরিমেন্টসে you get some radioactivity questions ওগুলোর জন্য কিছু ডিসকাস করব and definitions গুলো দিব okay so I'll give you a break and then we'll start after 5 minutes আচ্ছা okay
Recording in progress.
Lock it in here. Next week, the first set next week. Um, it's circular motion, gravitational field, electric field, those. All right, so these are some of the definitions out there. There's something that I need to address here. This is experimental. It's based on experiments that you might get. Okay, so it's an experimental thing, but paper 5 আসার চান্স বেশি, পেপার 4-এও মাঝে মাঝে জিজ্ঞেস করে। এটা ও লেভেলস অ্যাকচুয়ালি পুরোপুরি ঠিক মতন শেখানো হতো না, সো এটা তার জন্য ও লেভেলস একটা মিসকনসেপশনকে ক্লারিফাই করবো। How many? 3 years. Any bunch of 3 years is fine, because within 3 years, if you do all variants, right, you will basically find variations of different types of experiments, magnetism, thermal, oscillations. So if you do any chunk of 3 years, right, it should give you exposure to all the types out there. So any chunk of 3 is good. Most recent is better. Yeah, I'll be doing from 19 till 23. 24 just for practice report. Okay, so how do you find the activity of a sample? Okay, it's a very straightforward question, but it answer actually quite complicated. So let's have a sample here, and I want to find the activity of the sample. So first of all, sample randomly you have to keep the sample where? In a protective casing. Do you know what the casing is like? Yeah, it's a lead casing. Okay, so you have this casing here. We casing bhitor sample take rakhte hoy, and inside the casing you have your radioactive element. So it could be like, you know, uranium, whatever the rock is, ota can thake. Otar samne you have like this piece of lead cover. So a cover take hocche amra shorale hocche we can get access to it, then we can keep it closed like that. So that's called a protective casing. It's made up of lead. Lead blocks the most radioactive elements out there, radioactive particles out there. To measure the activity, ki use kora hoy. To measure radioactivity, right? What device do we use? Yeah, GM tube and counter, right? Geiger-Müller tube and counter. So it is basically aeroconnector rod thake, like a probe, and ওই probe-টা হচ্ছে is connected to a circuitry, and then that is connected to usually a counter. So counter টা হচ্ছে একটা screen হতে পারে with numbers on it, or it could be like a machine that makes sound. So originally, back in the day when they made the first Geiger counters, they used to give a click sound. Like every time a particle hit the counter, it produced like a click sound. So by hearing the click, you can figure out how much the radioactivity is. So let's say if you're next to a sample that's not very radioactive, you'll be hearing something like this. That's like normal, you know, maybe background radiation. Let's say the sample is very radioactive, right? And there's a lot of particles are coming out, right? So this is the GM tube and counter. So counter dekhe thake. Now, if I want to find the activity here, what I do is I take my counter and I place in front of it, right? But that doesn't give me the answer right away. There's actually a problem here. What's the issue? Exactly. Okay. So when you open this here, let's say, and there's radiation coming from here, and the radiation enters your chamber. This is actually getting mixed with or contaminated with what radiation? Background radiation. So wouldn't you get a wrong answer? So how do you fix this? How do you correct your sample's activity? What do you do? Yeah, so you first find the activity without the sample. That's your background radiation or background activity, and then you subtract that from your sample. Okay, so experiment করার আগে precaution হচ্ছে do the experiment in a place, or take the GM tube or counter to a place where there's no radioactive sample, find the activity, and then subtract it from here. Okay, but the problem that we never address in our A-levels, that they just randomly, brings it up in your MCQ, not MCQ, sorry, marks game, is that the GM tube, right, never actually measures the correct activity. What's the reason behind this? So the reason behind this is, at O-levels কেউ জিজ্ঞেস করে নাই, but জিজ্ঞেস করা উচিত ছিল, একটা স্যাম্পল থেকে যখন পার্টিকলস বের হয় কোন দিকে যায়? every direction imaginable. Okay, 360-degree, every single direction the sample is releasing particles. Your GM tube and counter, right? Is it capable of capturing all the particles, or is only capturing the ones that are in its direction? In its direction, right? Do you think then the reading would be an appropriate reading, or will it be an underestimate? Is how do you fix this? Is this the right value for your activity? No, right? When আমার হচ্ছে, imagine there's like a fountain and there's water flowing out there, and I hold a cup, right? And there's water falling in the cup. Is it true to say that all the water in the cup is all the water from the fountain? No, right? Am I not only capturing a small fraction of it? So how do I know what's the total amount of water that's coming out from the fountain? Or in this case, how do I find out the total activity? কি করা যেতে পারে? Sometimes students can figure it out on their way, right? Exam jigesh korlo and they can figure it out, but I don't want that surprise for you. Oh, redirect them back to so these are alpha beta, right? So when they hit a surface, they get absorbed by the surface. Redirect method, what is key? Right, very good. That's exactly what we do. Okay, so the way we do this is we use ratios. That's a chemical ratio use kora hoy. So we know that this small area here is capturing X amount of it, right? Now, a question there's a sphere like this, and there's a hole on the sphere, and this area in the hole of the sphere is provided to you. Wouldn't you be able to do ratio and then figure out how much is the area of the entire sphere? But আমি তোমাকে যদি একটা small fraction provide করি এখানে, wouldn't you be able to use ratios and figure out what the area of that other thing would be? কেমনে করতে হবে একটু দেখাই তোমাদেরকে. Imagine this part that you see here, right? It's a small area here. It's circular. This is the opening of your what? GM tube. So this is pi r square, and you know the location at which this is placed, right? কত দূরে দেওয়া. So the distance is d. Wouldn't that be used to find out the surface area of the sphere? So what's the surface area of a sphere? Yeah, 4/3 now. What is the surface area of a sphere? Surface area of a sphere? No? But don't tell me the night over there. Of course, it says. Yeah, 4 pi r square. So surface area of your sphere is 4 pi, you can have a d square. So if pi r square gave you an activity of, let's say, 20 becquerel, right? Wouldn't you be able to then do the math with 4 pi d square gives you what amount of activity? Because we are assuming that the radiation has been distributed in what manner everywhere? Evenly, right? Which is not true, obviously, but at least we're getting a better number here because এখানে কিছু যাচ্ছে, এদিকে কিছু যাচ্ছে. So যে fraction এখানে যাচ্ছে, আমরা ওই same fraction টাকে apply করে দেখতেছি what's the total amount that's coming out from the sample. Okay? Now, the good news is, তোমাদের হচ্ছে এখানে GM tube and counters, modern day ones, right? What do? They actually make this calculation and show you the value. তোমার manually করতে হয় না. So when you take a GM tube and counter, the number that you're seeing is actually the what value? The estimated full value. So ওরা ওটা distance wise, they can figure out that what should the activity be. But তোমাদের paper 5 ওই experimenter মধ্যে থাকে না the improvements and precautions, ওইখানে they mention about this fact that students need to write down about the fact that the corrected value from the sample has to be calculated using ratios. So এটাই ব্যাপার করা হয়. And paper 4 এর মধ্যে there was a year when they asked that a student experiment করতেছিল, they found the activity, why suggest 1 or 2 marks, why is the answer not like correct, why is it the wrong activity? So এখানে অনেক answer ছিল. একটা তো obviously there's what radiation, background radiation. Number 2 হচ্ছে that the sample is contaminated. Number 3 হচ্ছে এটা, that the ratio was not proper, you're only taking a small fraction of it. It's like a follow-up question, Chilo. Since that question came up, I want you to try. Can you tell me why is it possible that a sampler activity is more than what you anticipated? From a math problem, we got an activity, right? I take my GM tube and counter and I hold it in front of it, and the activity is way more than what we predicted. Why could that be? What could be the reason behind this? It's actually very common that this thing happens. Back into the sample. then but the thing is that that would cause a reduction, right? But this is an increase. Yeah, we are seeing that the sample's activity is more than what we anticipated. Less এর জন্য অনেক কিছু বলা যায়, সব নেওয়া হচ্ছে না, the point that the counter was not placed in the appropriate location. There are a lot of factors out there. Yeah, even after background radiation is corrected, you find that the activity is higher than what it should be. Lower region artery reason key. What if it's like alpha radiation? Alpha radiation has a very small range, right? Your GMQ and counter was what? Not close enough. That could be a reason. But no, this is something different. What could be the reason for a higher value for your count rate?
So the radiation hits a multiple time.
No, once it hits the GM tube, it absorbs the radiation. So it's not possible for it to show up again. Yes, online there are both two answers are close by. Anyone else?
So is it when
Very good. That's the exact answer. Okay. So we always forget the fact that if you have a sample and it's radioactive and it decays and forms something else, right? The thing that it decays into can also be radioactive. In some cases, it can be what radioactivity? Higher radioactivity. It's more unstable, or it's emitting particles at a more higher rate. We forget that because when you hold your GM tube in front of a sample, right? Is it only picking the radiation from one sample, or is it taking it from the whole thing? Whole thing, right? I can't isolate yeah, it decays into other things decays to other things. So basically when you have a sample, it's actually a contamination of many things out there. So আমরা যে ম্যাথগুলো করি রিয়ালিটিতে এটা করা খুবই complicated, because whenever I give you a uranium sample, right, it can't be 100% uranium. If it's 100% uranium, you'd be in jail, because that's called enriched uranium. You're not supposed to be in possession of that, and it can turn into a bomb. So আমরা যে uranium পাই, what is it? Contaminated. It's contaminated with uranium 235, 238, and thorium. Thorium কোথা থেকে আসছে? Uranium decays to thorium. ওটাও তো এখানে আছে. Then you'll find a bit of lead inside it as well. Where did the lead come from? Thorium will decay to radon, radon will decay to radium, radium will decay to lead. ওগুলো সব হয়ে গেছে. You can't stop them from happening, right? So whenever you get a sample, generally speaking, you're getting an activity that's a combination of everything out there. Okay? Clear about this? So these are the reasons why your activity can be higher or lower than what we anticipated. A practical aspect of it. It's not possible. So the thing is that for practice purpose, for demonstration purpose, we choose samples that decay to form an element that is not very radioactive. So in that case, you know that the byproduct is not actually contributing much, but it's generally very difficult, because whatever it's generated will also keep emitting radiation throughout. There's one advantage though. Eta kora jay, since you asked this, alpha decay jonno eta alpha decay na uranium er jonno is possible. Uranium decays to thorium through alpha decay. Thorium undergoes beta decay. So তখন যেটা করা হয়, আমরা we take our GM tube, right, and we place it like 20 centimeters away. If you place it 20 centimeters away, right, what can only reach your detector? The beta particle. The alpha is filtered out. By that, you can isolate the activity of one or the other. But if it's not alpha and beta or beta, then you can't, because it's mixed up. Is this okay? So I'll just add about this here. So yeah, we are done with radioactivity. On their next class, I'll start medical physics. Okay. Tomorrow Saturday, I was planning to take a test. On the December test now, I don't know. So I will take the last test I took was on magnetism, I think, or the book one, right? Okay, this test will be on quantum physics only. I'll let you know. It's Saturday or Monday. Yeah, today I'll complete everything. Yeah.
Can you explain to me how they allow that to happen?
Oh, what happened?
What's it?
Recording stopped.